so welcome everyone. So today our speaker is Enrico Cinti, who is finishing his PhD in philosophy of physics at the University of Geneva and the University of Urbino, and he's at both places. And he's visiting here the IOP and also the ILLC until the end. So he will be here until the end of October. And he's talking about space-time emergence inside black holes.
Thanks, Wilson. Thanks, everyone. It's a very lovely seminar. I'm very happy to be able to speak here. So it's going to be, I think, the first time that I present this material. So I hope it's not too rough, but anyway. Okay. So I hope it makes sense. Basically, what we're going to talk today is something that in philosophy of physics is called space-time emergence. And the basic idea is that in many approaches to quantum gravity, they seem to suggest that in some sense, space-time does not exist at whatever the fundamental level of reality described by quantum gravity is supposed to be. And the idea is that in philosophical parlance, we say that this means that space-time in some sense is supposed to be emergent. What is this?
That is every time someone joins.
Oh, okay. It's like an elevator. Huh? Okay, well, that's nice.
It's possible to remove it.
No worries. This is one of the main issues when people try to do philosophy concerning quantum gravity. This is one of the main topics that people think about. And the main reason why people are worried about this is that it comes from an issue called empirical incoherence. And in quantum gravity, it was initially discussed, at least in philosophical literature, in this paper by Haggett and Guthrie. And the idea behind empirical incoherence is that if we wish to understand measurements, basically, observations, it seems that observations require some sort of localization in space and time to be made sense of, like practical experiments seem to require space and time, localization in space and time. Otherwise, it seems that we cannot make sense of things like the experiment started at a certain time, finished at a certain time. The experiment happened in Amsterdam instead of Geneva. Things like this without space and time seem to be rather meaningless in a theory like this. And the usual answer that people give in this literature is that space-time in some sense can be emergent. So the idea is that we don't really need that the fundamental level of reality needs to be spatio-temporal to make sense of observations. We just need that the derivative level where the experiments themselves take place in is spatio-temporal. And this seems to be reasonably accomplished if we can, for example, recover general relativity in the appropriate limit. And so we can have this emergence relation. So just to give you an idea of some of the options that people have discussed in this debate. So this is arguably the most well-accepted one. This is functionalist idea that Chris Wutrick, again, with Vincent Lam, have suggested. And they suggest for a form of functionalism, they call it functionalism. The idea here is that basically we identify space-time by the specific theoretical role that it plays in a certain theory. And then we basically look for an appropriate object in quantum gravity, an appropriate derivative object in quantum gravity that fulfills that role in the appropriate limit. And then we say that that object is space-time. Now, the idea is that this is supposed to be an instance of emergence. So we're not simply saying that there's something that approximates space-time. The idea is that due to the functionalist slogan, that basically here becomes space-time is as space-time does, the idea is that in that limit where we have this object, that object is actually space-time. And you basically avoid, again, empirical incoherence the way that I was mentioning before. So you basically have an appropriate regime where you do have space-time in some sense. And so you can use that spatio-temporal background to define experiments and things like that. Now, a slightly different suggestion has been this by Sam Barron more recently, and he calls it eliminativism about space-time. And the idea here is kind of maybe on a slightly different note from the usual emergent approach, in that what he wants to say is that the status of space-time in general relativity is analogous to the status of something like Galilean space-time in special relativity. So Galilean space-time in special relativity people usually do not wish to say that it is an emergent spacetime, so that there are two entities, Minkowski spacetime and Galilean spacetime, and one emerges from the other. Rather, people want to say that in the appropriate regime, for example, where velocities are very small, then Minkowski spacetime approximates Galilean spacetime, or something along these lines. And the idea that Baron has is that we should try to do the same thing with regards to quantum gravity. So the idea is that there is, strictly speaking, no spacetime, but in the appropriate regime, the quantum gravity structure that we are looking for basically arbitrarily approximates whatever spacetime notion that we wish to recover. And again, the idea is that then you solve empirical incoherence basically in this way by making sure that there is a quantum gravitational analog of whatever notion you need to make sense of your experimental data. So things like localization, maybe some approximate notion of time and something like that. You basically wish to approximate them arbitrarily well. So in this sense, it is an intermediate approach between emergence, let's say, and a more straightforwardly no space-time view. So what I want to do today is that I want to basically look at some of the ideas behind these constructions, behind these philosophical proposals regarding the status of emergent spacetime in the context of the ADS-CFT correspondence. So in the context of basically what, as of today, I think is still the best, most well-developed option for a holographic approach to quantum gravity. And in particular, what I'm going to look at is basically the construction of the interior of a black hole in this context. And I'm going to argue that when we look at the interior of a black hole in the ADS-CFT, then it seems that emergence is simply the wrong notion. We cannot make sense of emergence for a variety of reasons that I hope I'm going to be able to explain. And that what we get is something much more extreme than what even Baron suggested. We get this notion that I call the only way that we have to make sense of the relation between general relativity and quantum gravity is with a notion that I call operational recovery. And operational recovery basically says that only operational data makes sense when it comes to the semi-classical regime of ADS-CFT, at least, again, the specific context of the interior of the black hole. So the idea is that this is an in general claim. In general, we can make sense only of these things. In specific context, we might be able to make sense of more than this. But in the interior of the black hole, this is all we have. And I will also suggest two basically metaphysical glosses, let's say, on this notion of operational recovery, which I call operational eliminativism and operational emergence. And the idea, the main difference behind the two is whether or not you think that it makes sense to reduce space-time to purely operational data. If you think that it makes sense, then you will do something like what I call operational emergence. Otherwise, you will do something like operational eliminativism. And I'm going to briefly explain how, using these notions, basically, you can still avoid empirical incoherence. So let me just give a very quick background on basically what we mean now by ADS-CFT and how to describe the interior of the black hole in this situation. So the idea is that ADS-CFT is a certain duality, roughly speaking, an equivalence between theories, between anti-de Sitter space-time in n+1 dimensions, where anti-de Sitter space-time is the maximally symmetric solution with negative cosmological constant of the Einstein equations, whereby maximally symmetric I simply mean that it is basically the solution with the most symmetries consistent with the Einstein equations, with the most possible symmetries consistent with the Einstein equations. And then a conformal field theory in n dimensions that we can think of as living on the boundary of this ADS spacetime. Now, insofar as we believe that the CFT is well-defined non-perturbatively, and at least compared with quantum gravity, we at least have an idea of how a CFT, which is just the quantum field theory, can be well-defined non-perturbatively, then we can take this duality to provide a non-perturbative definition of quantum gravity in ADS spacetime. Now, of course, ADS spacetime is not the spacetime relevant for cosmological applications, but it is at least a reasonable approximation to what we might want to do with a black hole. And at least it gives us an interesting theoretical playground to test some ideas about quantum gravity and see how they work. So again, we can use the CFT to define the non-perturbative dynamics of the theory. at least in principle. And for this reason, I will basically speak of CFT or fundamental description, and I will speak of ADS or semi-classical or effective field theory description, since in ADS, I'll be concerned only with the basically effective field theory of gravity in the bulk. And just as a disclaimer, like there is no claim of relative fundamentality that is intended by using this language. So the idea is that the boundary theory and the bulk theory are perfectly equivalent. There is, in principle, if the duality holds, it's an exact duality. So I do not wish to say that the CFT is more fundamental than gravity in the bulk. I simply wish to say that for the purposes of today, we take the degrees of freedom that we, as of now, can only describe with the CFT to be the fundamental degrees of freedom, and the semi-classical degrees of freedom that we know how to describe with gravity to be the supposedly emergent or at least effective degrees of freedom. So basically, I now want to very briefly again explain why, in some sense, at the fundamental level, it seems that we can say that ADS-CFT involves some kind of non-spatiotemporal notion. And the reason is basically this. First of all, insofar as the duality holds, whatever the non-perturbative quantities that we're going to deal with are, the fundamental quantities are going to be, they're going to be dual to CFT quantities. So at most, they will depend on the conformal structure, which is quite a lot less space-time structure than we are used to from general relativity. Indeed, something more is true in that if we take the common core approach that Sebastian, for example, has developed, where we basically wish to say that we should take as real only whatever is invariant between the two sides of the duality, it seems that not even the dimensionality of space-time is a given fact. For the reason that I was telling you before, we have n+1 dimensional gravity in the bulk, but we have an n-dimensional CFT in the boundary. More in general, we expect ultimately gravity in the bulk to be full quantum gravity. So we'll have arbitrary fluctuations of the metric and things like this. So we presumably cannot give a straightforward space-time interpretation of those quantities, at least where space-time interpretation means something like a 4-dimensional Lorentzian manifold or something like that. And so it seems that whatever the fundamental degrees of freedom in ADS-CFT are, they will be to a more or less large degree something that is not straightforwardly spatiotemporal in the way that we are used to, at least in general relativity. You might wish to say that space-time is more than what is in general relativity, but for today we will take just this. So how do we relate the semi-classical and the fundamental picture in ADS-CFT? The way that we do that is basically through this program of bulk reconstruction. And the idea behind bulk reconstruction is that we wish to start from the CFT quantities, so from the CFT Hilbert space and its operators. And we wish to define a map that tells us how to recover from these CFT operators the semi-classical gravity effective field theory operators and quantities. Basically, we wish to learn how to embed the space of states and quantities of the semi-classical gravity in the bulk into the CFT Hilbert space, so that we know basically how the fundamental and semi-classical descriptions are connected. So in particular, we will end up with a description of how local bulk quantities are represented in the non-perturbable definition of quantum gravity given by the CFT. And so this is quite crucial for emergence, exactly because it tells us how to connect semi-classical gravity with non-perturbative data in the CFT. So the crucial concept here for bulk reconstruction, at least in recent years, has been this notion of entanglement wedge reconstruction. And to cut a very long story, very, very short, without giving basically most of the details here. But the idea is that given a certain spatial subregion B in the boundary theory, so in the CFT, there is a certain bulk region, which we call WB, which it can be defined precisely. We're not going to do that. such that this conjecture is supposed to hold. So all physical quantities in WB, operators, states, whatever you want, are represented in CFT by certain operators and states in B. And the idea is that the map between WB and B, between the Hilbert spaces, is linear, but it is not necessarily an isometry. This is in a sense, some of the stuff that's come out more recently. It is not an isometry in the sense that it does not necessarily preserve inner products, and this map is supposed to be evaluated in perturbation theory around Newton's constant, so in gravitational perturbation theory. The idea that it is not an isometry, while it is most of the time we can ignore it, it is crucial, and we are going to briefly see why, when we deal with interior black holes. So this failure of isometry becomes important, as I said, in the interior of black holes. And the reason why it becomes important in the interior of black holes is that basically, when we are dealing with operating black holes after the page time, non-perturbative corrections to this map, which instantiate these violations of isometry, lead to the possibility of recovering the interior of the black hole from Hawking radiation. Now, this is a highly non-classical behavior in the sense that the radiation is supposed to be far away from the black hole at this point. It's supposed to be old radiation that we have collected at infinity in some kind of reservoir, for example. But thanks to these peculiar properties of the holographic embedding map, we can still recover information about what is going on in the interior of the black hole, which at this point is just space-like separated from the radiation, despite the two systems being in space-time quite different systems, quite distinct systems. And this is basically the Paris diagram that you get, where this green region is the region that you recover using the radiation, despite basically the radiation being located here. So strictly speaking, you wouldn't be able to receive signals from there, but you're still able in some sense to recover the information. Now, this is the way in which this enters into the interior of black holes. For simplicity, I will take a much simpler model, which is basically a toy model that is described in this paper by Hicker, Sengler, Harlow, Pennington, and Baradiana, which basically reproduces the basic qualitative features of this evaporating black hole, removing some of the complications connected to the fact that an operating black hole is a much more complex object. And basically all the results that I'm going to mention from now on are basically derived in their paper, so you can take it up with them if you don't like, well, if you're not sure of something that I say. So we basically take a quantum system, I, for interior, represented by a certain Hilbert space, and we can think of it as giving some kind of finite dimensional analog of the interior patterns of Hawking radiation. So basically, for all intents and purposes, of the interior of the black hole at a fixed, for a fixed Cauchy slice at time t. Again, we have no dynamics here, so we'll not implement dynamics. We'll simply look at a static model. And we also define a quantum system B with connected Hilbert space HB, which we think of as giving the fundamental description or non-perturbative description of the black hole system. So we have a semi-classical object, I, and a fundamental object, B, and we wish to know how they're related. How are they related? Well, there is a certain, again, linear but not necessarily isometric, maybe an approximately isometric map between HR and HB, which implements a reconstruction of bulk operators with this map. The idea is that these are basically bases for HI, these NI are bases for HI, and what we get back is an object in B, so this is a basis for HB, with some randomly chosen phases. The appearance of the randomly chosen phases is basically due to the fact that the black hole is supposed to be a chaotic system at this point. But basically, the structure of the map should be rather straightforward. Besides various details, the idea is that you apply this map two objects in the semi-classical description, and we get back something in the fundamental description. Now, as you can quite immediately see, given that this is the dimension of HB and this is the dimension of phi, V can only be an isometry insofar as the dimension of phi is smaller than the dimension of B. If the dimension of B is smaller than the dimension of phi, we simply do not have enough basis states in HB to ensure that V becomes an isometry. We basically do not have enough dimensions in B to account for all the possible distinctions that I can make in I. So it cannot be an isometry, it cannot preserve the inner product because it has to say that certain basis states or orthogonal states in I must have non-zero overlap in B. Otherwise, we simply wouldn't be able to embed I into B when this condition holds. And it is that this condition is exactly what happens, what holds when you have these quantum islands. Now, what Akers and colleagues show, nonetheless, is that if we take the inner product of two semi-classical states with the map, so we basically look at how their overlap in the fundamental description turns out, we get this. So when they're the same, we get one, as we should, and we get this reasonably small overlap when they're different. So while in some sense the map is not an isometry, it is close enough to an isometry. It is approximately isometric. And of course, we can also recover entanglement, edge reconstruction, and quantum island from here. Now we can maybe do slightly better than that. What Akers and others show is that actually, if we limit ourselves to states of what they call sub-exponential complexity, and the notion, the idea behind the state of sub-exponential complexity is that it is a certain state in our Hilbert space that we can prepare by using operations whose computational complexity is less than exponential. Okay, they do not have a particularly large complexity. The idea here is that technically, if you use a quantum circuit to prepare a state from a certain vacuum reference state, then the complexity of the circuit is going to be sub-exponential. So the number of gates in the circuit is going to be sub-exponential. Now, what matters for our purpose is, but besides the reason, is basically that in complexity theory, it is customary to associate complex operations with operations that cannot be carried out in practice, while sub-exponential complexity operations can be carried out in practice. So this is what we're actually worried about. As long as we limit ourselves to sub-exponential complexity, then this overlap is going to be very small, basically. We're not going to have a very large overlap between semi-classically orthogonal states. If we go beyond these complexity bounds, so if we were allowed to do exponentially complex operations, then we could actually see the failure of isometry. So we would be able to see that the map is not really an isometry and something has gone wrong in the semi-classical approximation. So basically, the idea behind this is that insofar as we think that any reasonable observer can only perform sub-exponential operations, which seems to be the case, at least in complexity theory, I think that this is a standard assumption, then basically whatever failures of isometries, whatever known semi-classical behavior the black hole might show will be beyond their reach and will not threaten whatever semi-classical reasoning they're interested in. Now, another thing that they show, it is not in this paper, it is still in the Akers et al. Paper, so something has gone wrong with the citation. But well, the same. They show that if V is not an isometry, then bulk reconstruction will be in general state dependent. These are basically going to be the two main characters, this complexity constraint and this state dependent notion. Now, by state dependence, the idea is that if the fundamental reconstruction of a semi-classical operator is going to exist only given a specific state. It will depend on the state that we choose. It will not, in general, exist for all possible states. The idea here is basically that this formula here, which tells us given O an operator in a semi-classical description, or O tilde an operator in a fundamental description, basically the fact that we can first apply our operator and then our map, or before we can apply the map and then apply the fundamental representation of the semi-classical operator, this equation holds only given a choice of a specific state phi. It does not hold for all possible semi-classical states phi. We need to choose one. And so for simplicity, we'll just write O tilde phi when we speak of the state-dependent operators. So the idea is that for different phi's, there will be different state-dependent operators that satisfy two. We will not always have the same operator because it will depend on the state that we choose. A consequence of this is that semi-classical operators will not be well defined in the fundamental description in the sense that they won't be linear operators, because an operator with the properties of the semi-classical operator will not exist. It will be a collection of operators, which in principle are all different. We cannot really glue them together in the appropriate way. In other words, O cannot be a linear operator in the fundamental description. You cannot have a linear analog in the fundamental description because for different phi's, we have different O phi's, O tilde phi's. And this in particular is going to be true when the dimension of B is much smaller than the dimension of phi. That is when we have these non-perturbative effects that become relevant and V stops being an isometry. Basically, we can think of this as a consequence of, again, of the fact that the map V is not anymore an isometry. Now, the point that is relevant is that this complexity condition and the state-dependent operators are not really in contrast with one another. Rather, they complement each other in making sure that despite this strange phenomena, these failures of isometry in the map, we can still have a well-defined semi-classical description. The idea is that we need state-dependent operators to accommodate these failures of isometry in V. And we need the state-dependent operators then ultimately to describe the interior of the black hole. That is where they become more relevant. The idea is that the operators in the interior of the black hole will be in general state-dependent operators. The exponential complexity constraint, the idea that we should limit ourselves to sub-exponential complexity states, basically ensures us that whatever consequences, whatever strangeness might emerge from failures of isometry and thus from state dependence is hidden from the semi-classical observer. So for all intents and purposes, the semi-classical observer is going to see a semi-classical description because they do not have basically sufficient resolution, sufficient computational power to actually check that the semi-classical description fails. Despite that, semi-classical description, strictly speaking, fails because we have state-dependent operators, which are not linear. So they're not, strictly speaking, well-defined operators in the Hilbert space of the theory. Now, what I want to do now is that I want to basically connect these ideas with emergence first and empirical incoherence second. So I will first discuss the connection between state-dependent operators and emergence, and then I will look at the connection between complexity and empirical incoherence.
It's 30 minutes now.
Okay, so I should definitely accelerate now. So emergence, basically, I suppose you're all pretty familiar with this, but is a phenomenon which encompasses these two usually contrasting aspects. One is autonomy, so the idea that emergent entities are in some sense autonomous from or novel with respect to whatever that they emerge from. And dependence is the idea that they ontologically depend on the microscopic entities from which they emerge. And the idea behind emergence is that we should have a relation capable of reconciling these two apparently contradictory notions. Now, a simple example is simply thermodynamics and statistical mechanics. So we simply take a physical system with a phase space m hat, each point in P, each point in m hat. P is a microstate, and we describe this behavior via statistical mechanics, for example. Now we can define thermodynamic quantities such as temperature or entropy as functions of phase space, and these functions will generally implement some type of coarse graining. So they will have, roughly speaking, the same values for a possibly large collection of microstates. Now we can quite immediately check how these two notions, dependence and autonomy, are implemented in this example. So dependence is implemented simply because we can take whatever the value of entropy or temperature of the thermodynamic quantities that we're interested in to depend on the value of the microstate, simply because the microstate is presumably more fundamental than whatever is going on in thermodynamic description, and the microstate fixes whatever the value of entropy is. Moving to autonomy, again, here it is the coarse-graining idea that is crucial, in the sense that what we see thinking about the coarse-graining is that these thermodynamic quantities do not depend sensitively on the specific values of our microstate. So we do not need detailed knowledge of the microstate. They simply depend, since they have the same value for a possibly large collection of microstates, they simply depend on certain, let's say, coarse-grained or large-scale features of these microstates. So in this sense, they are somewhat autonomous, at least from the details of the microstate. Now, if we have this example in mind, we can understand why these conditions fail in ADS-CFT, in the interior of the black hole in ADS-CFT. The first issue that we run into is with autonomy, because of state-dependent operators. So if you have state-dependent operators, the quantities in the semi-classical gravity description will depend sensitively on the details of the fundamental description, because exactly they depend on the specific state that we use to define the operator. The operator itself, the quantity itself, does depend on the state that we use to define it. It is not anymore the case, as in the thermodynamics case, where we could simply define these operators, these quantities, these observables for all states. Now we need to know which state we are working with in order to be able to reconstruct the semi-classical approximation. So we cannot have autonomy, because basically by specifying the relevant quantities, semi-classical quantities that we want to have, we are also basically fixing the details of a certain microstate in the analogy with thermodynamics. So we can.
Could you see this like the other way around? Because the semi-classical description is something you have access to, right?
Yeah.
Well, ideally, you would say that's something
Yeah.
that you can measure. So would that then, if at the fundamental level you have state-dependent operators, quantities, would sort of measurement or knowledge of the semi-classical description give you then insight into the state-dependent, the state that you are actually
so I'll maybe come back to this in the last section, but the idea, I would say no, because of this complexity constraint. So you cannot actually access this, you cannot actually see the fact that these operators are state dependent, because you cannot actually see the failure of isometry, because you would need to perform an exponentially complex operation to see that. So you cannot really have access to that. The point here, if you want, is that that would be very nice to be able to do that. That would presumably imply some kind of failure of empirical coherence, because you simply assume that there is no issue with empirical incoherence, of course. But insofar as you're worried about that, then it would seem that you have the non-spatiotemporal degrees of freedom that somehow define whatever is going on, that the semi-classical description has access to. and thus that they're not isolated from. But if that is the case, then it's unclear what even the measurement turns out to mean at that point. I should maybe mention this, that what ultimately now I'm suggesting is not the case, is that space-time is some kind of maybe theoretical construct is not emergent, where space-time is a theoretical construct can be understood as a four-dimensional, let's say, manifold, or as some operators in semi-classical gravity, for example. The idea that you can use operational data, in the sense you can do measurements on the semi-classical description and then simply say that, look, it's space-time enough for whatever I need. That is what I'm going to discuss later.
Sorry, I'm still a little bit confused with this.
Yeah.
So your point is that there's no autonomy because somehow it requires too much information from the microstate?
Basically, yes. You need to have knowledge that is too specific of the microstate to specify what these operators are.
Yeah, but how? Yeah, I guess then the question becomes a bit like, you know, how do you define that specificity? Right. Right. That, you know, if you make the contrast with thermodynamics or something, you know, what is?
Yeah.
You know, why is that more autonomous? Sort of. Yeah. How?
Yeah. Well, they're quite extreme.
Because there's still some dependence on microstates.
Yeah.
So. Is it coarse, like, you know,
yeah, how
measure?
how coarse should the coarse graining be in a way?
Yeah.
So Akers and colleagues are quite extreme in that they actually want to assume a single microstate for that, a specific state for that. So that is presumably as specific as you can get, and we can agree that at least that is is not enough autonomy. Now you can do something slightly different, which is that you can actually define, let's say, subspace dependent operators, not strictly speaking state dependent operators. This is not what they do, but you can. That was, I think, the original idea in the papers of state dependence. Now, what happens in those contexts is that it is true that you might at some point start to worry about, like, when is the coarse grained enough. The issue is that it is always less coarse grained than the semi-classical description in a way. So you never get a subspace whose dimension matches the semi-classical description. You never get a subspace that is large enough that you can say this operator is going to be the same for all semi-classical state. You're always going to have this, however small, dependence on the microstate. While in the context of things like thermodynamics, you do not have something like that. So you can say that entropy is the same function on phase space, independently of whatever microstate you end up being in. Now the value of entropy changes, so the output of the function is different, but the observable itself is the same. Now here what happens is that not even the observable is always the same, but it changes depending on the state that you find yourself in. Moving to dependence, here I hope the argument is even more straightforward, in the sense that we have seen that state-dependent are not linear operators. Dependent operators are not linear operators. We can assume that the minimal condition for some relation of dependence is that both its relata should exist. This, I think, is pretty standard in the philosophical literature on dependence relations, on metaphysical dependence relations. The idea here is simply that if you give me whatever the microscopic constituents of my entity are supposed to be, and they are arranged in the appropriate way, then whatever the emergent entity is supposed to be should be there. It cannot fail to emerge. Now, the assumption that is possibly controversial is that you also need to assume that for an operator to represent something that is physically well-defined and that exists, it must be a linear operator. Now, this is to some extent possibly slightly more tricky as an assumption, the idea behind this assumption is that at least if it is not a linear operator, then it is not a quantity that we can treat using the usual quantum mechanical rules. It is not something that we can use quantum mechanics as standardly defined to analyze. An interesting question would be to construct extensions of quantum mechanics that can make do with state-dependent operators. Still, it seems that, at least to me, failure of linearity in this sense tends to suggest that whatever we are dealing with is in some sense not really an appropriate physically well-defined quantity. And the idea then is that you can simply put together these assumptions and you get that the spacetime in the context of the black hole interior does not satisfy dependence because it is given by state-dependent operators, and these are not linear operators. And thus, they do not exist in a way. They do not represent something that exists. What they do represent, actually, as we're going to see, is that they represent observations, things that you can see and do. They do not represent, but these observations do not have an underlying well-defined physical entity that justifies those observations, not at least the underlying physical entity that the state-dependent operator suggests, space-time in this case. Okay, so this is what I was saying before. Okay, so the conclusion simply is that, in a sense, at least as long as we restrict ourselves to this very specific situation, emergence is not the appropriate relation to connect the fundamental and semi-classical description. Now, as I was mentioning in the introduction, the main reason why we wanted to have emergent spacetime was to deal with empirical incoherence, where empirical incoherence is the idea that a theory might undermine by its very structure the same predictions that we use to confirm the theory itself. And you can see this immediately in quantum gravity if you think that measurements require some kind of space-time background, and quantum gravity theories are non spatiotemporal. Then if you try to make a measurement in quantum gravity and quantum gravity is not spatiotemporal, then simply put, there is no well-defined notion of measurement that can be had in that context. And so it seems that whatever we can do to test quantum gravity runs into the contradiction that no experiment is possible there. Now, of course, the solution that was suggested is that spacetime is simply emergent and thus available to the entities that actually perform the experiments, simply not there fundamentally. So now, again, if we do not have emergent spacetime, then we seem to run into this worry that in some sense, we have no portion of reality that is insulated from these non-spatiotemporal effects, where we can perform measurements and test our quantum gravity theory, and then find evidence for it. Now, what is important here is that, as I'm putting the issue, and as the issue has been put, what is really the problem here is not really emergent spacetime. The problem is the meaningfulness of experimental procedures in a world without spacetime. Emergent spacetime is simply the most straightforward way to answer this question, but it is not necessarily the only correct one. Now, if you recall what we were saying before when we were discussing complexity, the crucial point here is that the localization of spatiotemporal properties are correctly recovered from the geographic map V using state-dependent operators up to exponentially complex operations. So the idea is that as long as an observer cannot make a measurement that is exponentially complex, then they won't be able to see the fact that they are dealing with a non-spatiotemporal theory. The word is not spatiotemporal. At no point the interior of the black hole is spatiotemporal, because, for what we said before, these are not really well-defined quantities. These are not really well-defined. These are not operators that represent well-defined properties because they're not linear. But our hypothetical observer will simply be unable to see the fact that there is a failure of well-definedness of these things. And so basically, as long as they're limited to operations of sub-exponential complexity, then whatever they will be able to learn about the world around them will be indeed spatiotemporal, will look spatiotemporal. We summarize this point basically with this notion that I call the operational recovery, which is a summary of what I just told you. So as long as experimental information can be defined appropriately, in terms, for example, of observables that at least give out results that are those of semi-classical gravity, then there is no problem of empirical incoherence, independently of whether or not space-time is emergent, simply because what we were worried about initially were the experiments themselves, not necessarily space-time. Space-time was simply a route to get there. Now, to come to the very quickly to the two metaphysical glosses behind this, depending on where you fall or whether you think that this operational data that you can actually have in this context is sufficient to recover space-time or not, you're going to either have operational alienativism, which is the idea that there simply is no such thing as space-time, and simply quantum gravity degrees of freedom give an arbitrarily good approximation to the observational data, observable data, that would be typical of a space-time theory. And in this way, they avoid empirical incoherence. Or you can think of operational emergence. If you think that space-time can be reduced to observation, to this kind of observational data, then we can meaningfully say that that experimental data is emergent, and so in the sense that space-time is emergent. And this is due to the fact that complexity hides the non-isometric nature of the holographic map, which gives us which allows us to avoid empirical incoherence and basically gives us, for example, autonomy back. And you can do roughly the same argument with dependence. The idea is that once I have said that the relevant notion of existence for space-time is an operational one, I've reduced space-time to operational data, then I am allowed to use the fact that my measurements cannot see anything beyond the semi-classical data to argue that whatever I am measuring is not sensitive to the operational procedure that I'm using, the measurement procedure that I'm using is not sensitive to the microdata. Despite if I wanted to define something more significant than that, if I wanted to say that behind that operational data, so simply the fact that there is an observable that outputs the appropriate relation, there was something like space-time, then I would have needed that observable to not simply give me appropriate results, but rather I would have wanted it to have a consistent description on my space of states. So in particular, we would be mistaken in the sense in saying that there is emergent space-time in the sense of a four-dimensional manifold, since it's not well defined to the state dependence. But we can speak of emergent space-time in the sense of a certain pattern of observational data obtaining, since such observational data is, thanks to complexity theory, well defined, and in this sense it does not depend sensitively on the fundamental description. Okay, so these are simply conclusions. So how long have I gone, Sebastian?
So you're at 15 now, 15 minutes.
Yeah, I mean, I think we can close there. Just simply some open questions regarding the development of this notion of operational recovery. So what would be interesting would be, of course, to give a precise analysis of space-time in operational terms to see whether or not operational emergence is viable. Would be interesting to see the consequences for the foundations of general relativity of these ideas, in particular for the global space-time structure GR. And also it would be interesting to connect these ideas to effective field theory, which is something that I have not discussed. So whether or not effective field theory is usually taken to instantiate emergence, whether or not these constructions are effective field theories or not. And then it would be very nice to have an interpretation of state-dependent operators that can give some sensible, well-defined foundations for them. And that's it. Sorry if I went a bit long.
Right, you can ask some questions. So I have a sort of more general question, and then I ask a specific question. So let me start with the general question. So your argument here about emergence or not emergence is very much taking the black hole as an example.
Yeah.
Okay. Now, I've said at many talks on string theory about these things for the past 10 years or something. And I know for a fact that, this is still under development.
Yeah.
Like many people don't even agree on this possibility of state-dependent operators, exactly because of things like you said, like it violates the quantum mechanics we know, et cetera, et cetera. So, and the page curve, all that stuff is still like there's a lot of puzzles there that we still don't understand. So you're making your whole argument about the emergence of space-time based on the most exotic object that we know and we still don't understand, while we understand very well how to reconstruct space-time with other, not state-dependent operators that don't involve black holes, right? Yeah. Entanglement entropy, all this kind of stuff. So I find it a little bit too much to conclude such things based on a developing field in which we representing we, even though I don't work on this, we string theorists still don't agree about these things.
Yeah.
You see what I mean? Because
no, I see. So yes, I see. So the answer would be this. No, I mean, it's true as you say, of course. Yeah. So the thing would be this. It would be twofold. So first of all, what seems to be interesting here. So the thing is that more generally, we can roughly, well, you're right that in certain cases it is much more well understood, but it is still the case that roughly speaking, one could leverage these kind of objections basically to any attempt to study, to do some philosophical work on quantum gravity, right? You could say that also of string theory, to simply say, well, but we have no empirical evidence in favor of this. Yes, it is much.
No, I'm just talking about the math.
No, I'm not.
Duality, I can reconstruct the bulk. There's a lot of cases we can do with all this technology. About the black holes are really the biggest puzzle of this whole thing.
No, but I didn't want to say that this was like what you were saying. I'm saying that like the same objections I've heard it said like just about in general quantum gravity. Now, the answer to that is simply that what seems to be interesting in this case is simply to explore the space of possibilities here. So what is the models that they're getting at now, it seems to me like this stuff that they're doing now is not as well defined as what you were saying before, but it is reasonably well defined. Like it is not this use of approximately isometric codes with complexity is not as well defined maybe as standard entanglement wedge reconstruction. That's true, but it is not that far off from standard entanglement wedge reconstruction. It seems to me, from what I understand of the literature. So the thing here now is that it seems that what is reasonable to do is to basically chart the space of basically logical possibilities that can obtain and see if we can find some avenues for understanding the relation between space-time and quantum gravity that is new compared to what the literature thus far has suggested. And the literature thus far has suggested if you actually, some people in the philosophical literature on this have even suggested that only the functionalist approach is the only one possible, and that is clearly not true. But even if you take that, if you don't believe that, it seems that what you want ultimately is to have alternatives so that whatever the theory that you end up with, you can actually you have an idea of how to approach this difficult question of how space-time emerges from quantum gravity. And moreover, what you also want to do is that, if possible, you want to have, at least my idea is that, if possible, what you want to have is to have some kind of example to show how this kind of relation might be instantiated, even if the example, as you say, is at the very least extremely exotic. It is extremely exotic. But the idea is that it illustrates something interesting about how space-time and quantum gravity might be connected. It's not, you shouldn't take what I said today as an endorsement of these specific models. It's just, this is a possibility, this is how space-time might turn out to come from quantum gravity. Now, whether or not it is the correct way, it might come out of quantum gravity, of course, is an open question.
Yeah, I'm just concerned about the generality of the claim because it's it's just something we don't understand very well mathematically even, and then using that to make a claim about whether or not space-time is emergent in this circumstance. I just don't feel too comfortable about that, but that's my point of view. So if there is state dependence, if that's the way it works, etc., I understand the steps towards some conclusion, but not putting the whole ADS-CFT into that conclusion. That's
okay. I see what you're saying. There is a big caveat that sometimes was there, sometimes in the slide that you don't put it to take too long, but it is the caveat is that it is the specific example that he used to. Now, of course, if the specific example turns out to be correct, then which is a big if, then I mean, you can even say that, again, it is at most an in general claim in the sense that in general in ADS-CFT, it is not the case that emergence is correct, but of course you could say that emergence is still in some sense the correct notion when you're dealing with the more germane cases where you're not trying to reconstruct the interior of a black hole, basically, which would be in and of itself an interesting question, like how sometimes something can be emergent, sometimes the same thing can be not emergent. But yeah, I mean, the idea here is simply to make it, the general point is the philosophical point that things like this can, at least in principle, happen. It is not supposed to be a general point that the ADS-CFT is definitely this thing, and we are completely sure that this is the fundamental description of how things go in ADS-CFT. That was not my intention.
There's some questions in the chat. So here, consensus.
Should I open the chat?
Or maybe he wants to unmute and ask himself, because we can.
Enzo?
Oh, yes. Hi to everyone. Can you see and hear me?
Yeah.
Okay. Thank you very much for the wonderful talk. I have only two small observations. One is that I'd like to understand better whether the notion of emergence implies the possibility that what emerge modify without that what is at the low level modify, because if this is not possible, perhaps the word autonomy is a little too strong. It would be better to speak about diversity, in the sense that what emerges is different from what is at the basis. But I don't know, because for instance, in the example of thermodynamics and statistical mechanics, yes, it is possible that at the micro level something change without that at the macro level there is a variation, but it is not possible the contrary. This is the first point. Second point, I don't remember which are the reason, because it is not possible to make experiment without space and time. Not all physicists, not all in the history of physics believe in the existence of space and time. Before 16th century, probably the notion of space and time as we intend were never thought by physicists in general, but I think that Ptolemy can do experiments without. I don't understand why it is necessary that space and time, in a sense, even if a week must be there to make experiments. Thank you very much.
Thanks. So yeah, with regards to the first thing, I think that the distinction that you have in mind is something that sometimes people call weak and strong emergence. So the idea behind strong emergence is that I don't know if they would put it like this, but let's stick with this. You can have this kind of diversity that you speak of. Also, in the sense that the emergent thing can do things that that simply have no equivalent in the base. So the idea is that people sometimes put this in terms of causal powers. So the idea of strong emergence is that the emergent entity has causal powers that are not had by the base entity. I think that the only example that at least people still discuss as of today stuff like downward causation in the philosophy of mind, which I'm afraid that I just mentioned something that maybe the audience is not familiar with, but the idea very roughly is that people make this, well, you've maybe seen this, people make these sorts of similar claims about emergence when it comes to the relationship between the mind and the body. And one thing that some people sometimes say is that the mind is strongly emergent on the body. And the idea, the way that you illustrate this is that there is this idea of downward causation in the sense that the mind, which is less fundamental than the body in the sense that it depends on the body, it still is able to causally influence whatever is going on in physical reality. A very stupid example, but gets the point across, is that sometimes you say that you have opened the fridge because you were hungry, and being hungry is the mental state. And mental states are not supposed to be, in principle, they should not be able to influence physical reality. But if you take seriously this way of speaking, then it seems that our mental states have causal powers, including the ability to influence physical reality in this direct way, in that they open the fridge, or they cause me to open the fridge. And these causal powers simply do not have a straightforward, if we want to postulate them like this, they do not have a straightforward interpretation in terms of neural fibers firing. So the thermodynamics case is not like this. It is a case of weak emergence, where we do not have these novel causal powers. We simply have some kind of coarse-graining thing. So in this sense, then yes, yes, it is true that you can have difference in the base without difference in the emergent entity, but you cannot have the opposite. You cannot have differences in the emergent entity without some respective difference in the base. I agree that you could decide to give it a different name. The use of people give different names to these things all the time. The use of dependence and autonomy, I think, is quite standard in the literature on emergence. I just to make sure that I was not choosing like two controversial terms, that is taken from the Stanford Encyclopedia article, where they say that you have these two possible notions, and then you distinguish emergence and strong and weak emergence depending on how you articulate autonomy and dependence, usually. As to the second question, yes.
So Enrico, you are speaking about weak emergence, not strong. All your discussion is about weak.
Both. Ideally should apply to both, but yes, in general, well, if weak emergent phase, then presumably strong emergent phase too. But yes, the idea is that the notion that I have in mind is the kind of weak emergence that is most naturally adapted to physical situations. The second question, yes, that is a very interesting point. I'm not entirely sure that actually Agate and Wuthrich give that many arguments in favor of the assumption that space-time is required for measurement. Though it should be noted that what they actually have in mind, also from like personal conversation, is something that is a lot weaker than that. What they really have in mind when they speak of space-time is something very basic, like some notion of things being here or there, some notion of things being at a certain time and not a different one. Basically, what they want to have is some notion of localization in space and in what we usually call space and time, but understood as weakly as you want to understand them. And that seems to really be required to make sense of experimental data. If I'm not even allowed that an experiment is taking place here instead of there, then I'm not even sure of what I'm being shown. But if there are people who have argued that not even that very minimal conception of spatiotemporal localization, let's call it, is needed, then if you have any references, I would be extremely interested in seeing those. So that would be lovely. But what they have in mind is something very, very minimal in this sense. They usually then instantiate this by speaking of four-dimensional manifolds and things like this, but really they have in mind this very minimal thing.
Enrico, I think we have to close because we're out of time.
Yeah, sorry.
Still some questions, I also have on myself, but
okay, we can.
You're still beyond.
Yeah.
So let's thank Enrico again.
Thanks.